Hello, this slide describes how we can arrive at the ideal gas law from empirical gas laws. This is not a theoretical deduction of ideal gas, but how we can conceptually figure out the basis for the ideal gas law. In the next module, we will actually derive ideal gas law from fundamental equations of physics. For now, we will use the empirical laws as the basis. So let's start with the Boyle's law as the starting point for understanding where the ideal gas law comes in. So we will particularly write Boyle's law at 0 degrees centigrade and a constant temperature and let's say 1 atmospheric pressure. And we can write that in the form of V0 equals to C0 over P, where C0 is a constant at constant temperature and mass. So this is simply rewriting PV is a constant in terms of a convenient expression where the volume is on the left side. Now, if I were to use this V0 in Charles' law, which we deduced in the previous module, V equals to V0 alpha 0 times T. And so where T is our temperature, which is a function of volume, our volume is a function of temperature, and V0 is the 0 degrees, volume corresponding to 0 degrees centigrade, as we discussed. And so now we can combine these Charles' law with the Boyle's law by stipulating that V0 is measured at 0 degrees centigrade. So now I can write Charles' law as equal to V equals to C0, which is from Boyle's law, alpha 0 times T, which is from Charles' law, divided by P from the Boyle's law above at constant mass. Because now we are varying the temperature. So we have now managed to combine Boyle's law and Charles' law into one equation where we have connected volume, temperature, and pressure together. So now we stipulate that this is done at constant mass. So that is the fourth variable we're interested in, varying. So we ask the question, how can we do that? So we will simply state that we can evaluate C0 by understanding how C0 alpha 0 might be related with the mass of the gas. For example, if we take our initial mass of the gas and keep the same volume and the same temperature, and now we double the mass, then the pressure should also be doubled. Or alternatively, if we keep pressure constant, temperature constant, and then double the mass, the volume should double. So we can very simply argue that C0 alpha 0, therefore, should depend on mass of the gas. In this case, we write this as W. So the alpha 0, C0, this is the product, should be a function of mass. But we know alpha 0 is a constant, it's independent of mass. Therefore, C0 should be dependent on the mass. So now we can write the combined Charles-Boyle's law in a form containing weight or the mass of the gas, W, as V equals to then C times W times alpha 0 T over P. Now this is C is a new constant we introduced instead of C0. So we don't know numerically what will be the value of C. And this is what we will be doing on the next slide. Okay. So in the next slide, we're continuing now trying to figure out the new constant C in the equation where we have combined volume, temperature, pressure, and mass of the gas. So this is now coming to look similar to that of ideal gas law that you have been taught before, except there are these strange quantities C, W, alpha 0, and we also recognize the number of moles N and R are missing. So we need to find a way to relate C, W, alpha 0 with number of moles and the gas constant, which we're going to do next. So for this purpose, we will define a characteristic mass of the gas. That is, we will say that each gas, by its chemical composition, has a certain mass. We call this molar mass. Okay? At constant conditions of pressure, volume, and temperature, we call them as P0, V0, and T0. And therefore, we can now replace W with M under these conditions. In other words, we write the above equation in terms of P0, V0, T0, and we replace W with M. Now V0, which is still the volume, standard volume, and is equal to, that is consisting of 1 mole of a gas, in this case, C times M alpha 0 T0 over P0. Note that we have M replacing W. So now we can readily calculate the value of C from this equation in terms of V0, alpha 0, T0, and P0 by simply rearranging algebraically. So we have C times alpha 0, the two together, P0, V0 over M, T0. So substituting this quantities into the top equation, we now get volume V, which is what we have in the beginning, equals to P0 V0 divided by M times T0. That's the C times alpha 0 portion of the equation, multiplied by W times T over P. That is the remaining portion of the equation on the top. So now we can define a new constant, because P0, V0, and T0 are standard conditions, irrespective of what gas we have in our sample. And therefore, we can designate that as a constant common to all gases. Okay. So if I define that way, the value of gas constant R, we can write V then equals to R over M W T over P. So now we're coming close to what it looks like in a familiar form. That is now PV equals to W over M multiplied by RT. What is W? Mass of the gas. What is M? Is the molar mass of the gas. So mass of the gas divided by the molar mass, we know is simply equal to the mole number. So we can now replace W over M with N. So then we can write PV equals to nRT. Now remember, R is defined as P0 V0 over T0 of standard conditions. So this is the simple connection between Boyle's law, Charles' law, and also Avogadro's equation to arrive at the ideal gas law. The way we introduced Avogadro's hypothesis in here is by defining a characteristic mass and concluding that the weight of the sample, or the mass of the sample, divided by the molar mass equals to the mole number. This is where Avogadro's equation has been put in place. So this way now we have a complete description of the ideal gas law. PV equals to nRT. Now since 1 mole of the gas occupies 22.4 liters or so approximately at 0 degrees centigrade and 1 atmosphere pressure, we can now calculate the value of R. So please do so before we go on to the next slide. In this slide, we're going to make an argument on how we can measure the molar mass of a gas, which was introduced previously. The molar mass of the gas, now we can relate to density. And now let's look at what is density. Density rho is equal to the mass divided by the volume by definition. And the mole number n is also defined as mass but divided by molar mass. So now we can see the connection. We can replace W with rho and V and relate it to the number of moles n. So PV equals to nRT, and that is equal to W over mRT. And W over m now can be now rewritten in terms of pressure equals to W over Vm times RT. The reason to write W over V is because we now recognize W over V is the density, rho, of the gas. So now in this last equation, I can now see clearly that I can replace W over V with rho. Therefore, I can connect the pressure of a gas with its molar mass and the density of the gas. So this very simple substitution from high school chemistry gives us P equals to rho RT over M. So if I can measure now the density of a gas and its pressure at a variety of temperatures, I can now calculate its molar mass. So that's exactly what we do in elementary methods of determining molar masses of simple substances, which are gases or volatile liquids. So we measure the density at different pressures at constant temperature. So rho versus P is plotted, and this should give, for an ideal gas, a linear plot shown on the right bottom corner where you have the red line. The slope of this red line is nothing but RT over M. So we know the temperature where we carried out the experiment, and if we now know what is R, then from the previous slides, then we can now substitute and calculate the unknown M. So simply by measuring the density of a gas as a function of pressure, we can obtain molecular mass of the gas. So this is a very profound consequence from the ideal gas law. So you can now see one very important application of ideal gas law. We can also recognize that most real gases may not exactly obey the ideal gas law. Therefore, the molecular masses we measure using this approach will have a certain amount of error. Nevertheless, the molecular weights obtained this way for most of the volatile substances is quite accurate. And so here is a bit of a problem I would like you to work out. And so we're giving the density of the gas, and we are giving the temperature, giving the pressure, and we're asking you to calculate what is the molecular mass of this liquid. That is, the liquid is made into becoming a vapor, and the vapor density has been measured at a given temperature and pressure, and we're asking you to calculate molecular mass. So this is a cool application of the concept of ideal gas law and how it can be practically useful in determining important molecular parameters such as molar mass. In the next slide, we spend a little bit of a time about the gas constant R and its units. This is particularly important for you to calculate quantities using R, and so problems are much easier to solve if we were to pay attention to this. And that is R is given as PV over NT, atmospheres, liters per mole per Kelvin. We can write those units very readily because you have pressure on the numerator. So we express that, let's say, in atmospheres. We have volume, let's say we express that in liters. And N is in the denominator, so that is per mole. N is the number of moles. And the denominator also contains the temperature in Kelvin, so that is per Kelvin. So the units for R should be atmosphere, liter per mole per Kelvin, right? So there is no need to memorize the units for R. So one can readily write the units of R simply looking at PV equals 10 RT. Okay, what should be the units for these physical quantities so that we can determine the units for R. So this is the illustration, very simple illustration, how you can figure out what the units are. You don't need to look it up every time you need the units. Go through this process mentally, and then you can write it out. Or you can write in a piece of paper, PV equals 10 RT, and deduce from it. And so this is a good way to figure out how to write units for a constant present in an equation. You can apply it to any equation in the future. Now in the SI units, we are a little bit strict. We don't randomly pick the units, so we use SI units. And so newtons per square meter, so that is your unit for pressure. Meter cube, that is your volume, and per mole per Kelvin, standard units. And therefore you have newtons, meters, per mole per Kelvin, and we can simply recognize Newton meters as joules, so joules per mole per Kelvin. And so you can do all these sort of manipulations, a variety of things, and then write your units in pascals and so on and so forth. And you can also determine the value of R, as I mentioned before, that simply equals to the standard state conditions. And therefore, you don't have to look these values up from the literature. As long as you know what the standard temperature, pressure, volumes, P0, V0, T0 are. Now, I would like you to look in the book and see what are these values, P0, V0, T0. It's nicely explained. If not, we can discuss those details. We're not sure about how to do this. So, as an assignment, I'd like you to calculate the value of R in the units of pascals, cubic meters per mole per Kelvin.